Yeah, okay. Thanks, Derek. Thanks, everyone, for being here. As Derek said, I ended up in the Department of Material Science. So we do computational material science and modeling and simulation of different materials. And what I'm going to talk about today is fibrous fabrics. So we're looking at structures that look a little bit like this. I'll show some more in a moment. And model them using the Lattice Boltzmann method, which is a kinetic model working on the mesoscopic scale, basically. And that allows us to sort of look at macroscopic properties of these materials that would be interesting for manufacturing and processing. So as Derek also mentioned, this is a PhD project of my student Fang Wang, and sort of we got interested in this because my colleagues Louis and Fei-Pang, they can actually make such materials. So this is our computational model. These materials actually look like this, right? So this is a non-woven filter, if you want. So this is produced by sort of electrospinning of fibers. So fibers are shot out from a nozzle and then just deposited onto the surface, and they give these random structures, so that's relatively easy and cheap to produce. And you can see these structures are on scales of microns, but eventually the material is something like you all know. It looks on this scale, so to say. This is a non-woven fabric in a sense. So we are interested in extracting macroscopic properties by modeling and simulation here. So what we do then is we sort of kind of like, because we're actually convincing our experimental collaborators to produce 3D images that we can actually use directly. What we do right now is we actually randomly generate these geometries to mimic the porosity that the actual material has. So this is our geometry that we use in the simulation. And we have done some studies on measuring the permeability of these things and the tortuosity and different materials properties. And now we're moving to multiphase fluids, essentially, because lots of these materials are actually used as filters. So you run the fluid through it, and it's typically a mixture of two fluids or even more. So there are some interesting applications, for example, for oil recovery, or if you still have a diesel car, although they're not as popular anymore, you probably want to remove water from your fuel, and that can be done with these kinds of things. Because these sort of, if you have droplets in oil, these water droplets would sort of attach to some of the fibers and then start coalescing, and then gravity can pull them out. But we need to have the right structure to make this work efficiently. Now, the problem is if you have this multiphase or multi-component fluid, you need to model it somehow. And the way we do this is using Lattice Boltzmann with this so-called Chan-Chan model. So we actually have microscopic interactions between two different fluids that live on a lattice, right? So the Lattice Boltzmann method works that you have sort of particle distributions on each lattice side that can move in discrete directions. And now we have two of those, sigma and sigma bar if you want, and those interact with some force. So that's a very simple micro model if you want for a multiphase fluid. And depending on what interaction parameters you choose here, the G, you can create a non-ideal equation of state. Right? So this is the macro equation of state in that sense. In addition, if you have surfaces in your system, which we have because of the fibers, you can actually use a similar way to model surface interactions with the fluid. And that's a way how we can control what we call the contact angle. Right? So if you have a droplet that sits on a surface, that is typically characterized by the angle that this sort of contact line forms with the surface. And that depends on what type of fluid and what type of surface you have. And we can actually sort of control this angle by choosing the right interaction parameters. Here, depending on how the two fluids here, the black and the white fluid, if you want, interact with the surfaces and how these fluids interact with one another, this gives us like a typical Young-Laplace law for the contact angle, and this has been sort of verified and validated by Sebastian Schmieszek and Jens Harting a while ago. So this is a model that should work for what we want to do, and what we're interested in now is actually how droplets sort of interact with fibers, right? And there's a couple of parameters or numbers that characterize what we have here, and two of them involve gravity. I'll just throw them away in just a moment. That's the bond number, which relates gravity or the gravity forces to surface tension, and then the Morton number, which combines it also with the density contrast between the two fluids. What we are more interested in the end is the Weber number, which is something that relates to the advective velocity to surface tension. That's sort of what right, basically controls how the droplets flow through the system, if you want. So there have been some experiments on this, so we always need a reference to compare and validate our simulations. So we have looked at this experimental paper where they have first started looking at individual droplets on fibers. So we started simulating this and modifying the contact angle. So we have done 3 different simulations with different contact angles. And not surprisingly, you can see if you have a contact angle that is smaller than 90 degrees, you can see that the droplet hits the fiber and then it can go around relatively easily, but it likes to stay on the fiber, so it just hangs on that fiber in the end. So it gets attached to that fiber, right? So whereas if you take like really the 90-degree contact angle, you can see it takes, well, this is sort of, this is like a visualization effect. It's not really getting slower, but you can now see that the contact line is actually moving around and then rejoining in a while. And then you get this typical sort of, and this contact line will now also start moving around, and you get a typical pinch-off event in the end. It takes a while. Will happen. So there we go. So now it's pinching off a little bit, remains on the fiber, but the rest of the droplet just falls through. And then finally, of course, if the droplet doesn't like the fiber, so to say, if you have a higher contact angle, then it's just going around. Actually, you could see very quickly it's actually separating into 2 droplets that then rejoin. Right, so we can sort of reproduce these effects with the model we have. And now we were basically interested in what happens if you have several fibers, right? So if you really have this medium where you have lots of these things on micron scales and you have 2 fluids in that system, how can we sort of, you know, say something about a certain material, or how can we optimize the material to have certain properties? And again, there's many applications here, for example, dyeing of textiles, which is actually a non-trivial problem. Printing these days is very popular again, and yeah, the filtering stuff, right? So we wanted to now look at the capillary phenomena in these systems, because when you have several of these things, you will get capillary effects, right? So, and to, again, study a simple model system, we started looking at 2 parallel fibers and look at how droplets basically change their shape, or what shape do they have when they sit on 2 parallel fibers. And there's this, again, experimental work on this, where they have observed that there's a certain morphology transition depending on the distance and the volume of the droplet, the distance of the fibers and the volume of the droplets. And that's something that we were interested in reproducing in this case. So we, again, used the Lattice Boltzmann method to simulate droplets on a fiber. And in this case, what we wanted to do is study these different morphologies and how they change from one to the other. So there's 3 different basic sort of morphologies that we have identified. The first one is a barrel-shaped droplet. That is when it's really still a droplet that has just spread out a little bit on those 2 fibers. Then there's something called the drop bridge. That's when sort of most of the liquid is in between the 2 fibers. As you can see here, there's nothing on the outside of those 2 fibers anymore, but it's still a convex surface here, so it's still round to the top in between the fibers, whereas then it transitions to a droplet column where sort of the interface here goes from first flat and then to concave actually between the 2 fibers. So these are the 3 different morphologies we wanted to look at. And to first sort of verify the model, we've actually done this. So this will work as well. So we have set up a droplet on the fiber and let it spread out. So okay, this is, yes, it's covered by this. So it's spreading out until it reaches an equilibrium state, right? So this is what we have looked at. And then we have compared that to a relatively simple theoretical model where you just minimize the surface energy. So this cross-sectional geometry is relatively, you can handle it. You can analyze what the area is because you can determine these angles, and then you can minimize the surface free energy, which depends on sort of the two contact angles here, or surface tensions, and the lengths of the respective lines here, right? So, and then we have compared sort of this very simple theory with experimental measurements and our simulation results, and we get quite good agreement between all three. So, and what we see here also is the length of this column is actually the same, depending on, it's like similar, if we start with a drop spreading out, or if we start with a column that's initially too long and that recedes into a droplet. So right here, we cannot see any hysteresis, so we have to look more carefully into this. And that's what we essentially did by looking at the morphology transitions. So we started out with droplets that spread, and then we also looked at the capillary pressure, essentially, or the delta P across the interface for this transition. And that's something we measure over time, and we can identify these peaks here. That's essentially where the sort of droplet-like shape goes into a column-like shape during this series. So this is the critical capillary pressure where this transition takes place. So this is something we have sort of recorded for this experiment, and then we've done a similar experiment. Well, this is still, yeah, this is a summary. We've done this for different volumes and different distances of the fibers, right? So you can see here, if you increase the droplet volume, then at some point you can see this transition to the column shape, right? Because initially it stays in this droplet, and then when the volume is sufficient, it spreads out further into the column-like shape. And something similar happens here depending on the distance. You can also see that transition happening here at different distances depending on what the size of the droplet, which is related to the volume, is. Then we did the sort of the opposite experiment. We started with this spread out shape and let it sort of retract to its equilibrium configuration. So that sort of looks like this. And look at the top one here. You can actually, the movie is quite quick, but you can see that there is actually this transition and it suddenly sort of pops over. I mean, maybe not suddenly, but there's clearly this transition visible here. So again, we have measured all this for different volumes and different distances, and you can see that the transition is actually taking place here. Not for all distances, but for some of them. And similarly here, we have transitions for certain sizes of the droplets. And based on that, we can now actually join these two experiments, going from droplet to column and back, and draw a full morphology phase diagram. So this is kind of like a summary for a basic contact angle of 0. We can observe all these different shapes in this VD morphology diagram, as we call it. And then we can also look at sort of the dependence of the capillary pressure, and you can actually see here, if we plot these curves that we saw here before, now forward and backward, it's a little bit difficult to see the arrows here. We can actually see for the red one and the blue one here, there's this hysteresis loop, right? So if we go forward, we go this way, and then backward, we go this way. So the transition happens at a different point. So there's hysteresis in the system, and what we are actually quite happy with is, if you see the gray symbols here, so this line is a theoretical result, essentially. The gray symbols are experimental measurements, and you can see that the zones here that mark the simulation results agree quite well with the experimental results. So there's some deviation here where this experimental symbols fall off, and that's probably related to gravity, which, as I mentioned earlier, we have sort of discarded, and obviously that plays a role at some point. But we're quite happy with this agreement, which suggests that we can actually use our simulations to now start predicting things. So if we, for example, assume that we can tune the contact angle to 40 degrees, we get a little bit different phase diagram where sort of the transition lines are actually shifted. So depending on what you want in your system, you could now start using this contact angle as a way to improve your material, for example. Right? So we can also control the size of the hysteresis loop and these kind of things. So this might be an interesting tool to sort of, help materials development. And that's basically the main result. So the conclusions are that basically I think Lattice Boltzmann simulations are a sort of really nice tool. I've been using it like for a decade now. And because what I like about it, it's kind of like built-in multiscale, right? So you start with a kinetic picture, and you get macroscopic results out of it, and you can couple it with micro-macro coupling or something like that. So you can do all kinds of multiscale modeling with it. And in this case, we have sort of started measuring capillary pressure for these droplet configurations on 2 parallel fibers, and sort of validated it against analytical sort of models and experimental measurements, which is a good starting point to actually look at morphology transitions. And now we want to go to the whole material, right? So now we want to really do random arrangement of fibers and then look at how these things could be used as filters. So that's sort of the little story here. What would be interesting to look also is the dynamic timescale. So we have not really studied the timescale because they could actually sort of then provide some insight into how the liquid actually redistributes into the filter. So again, I would like to acknowledge my colleagues who do make these materials. So hopefully they can actually at some point act on what we are sort of suggesting. And we get some funding from the National Science Foundation. So with that, I would like to thank you for your attention and happy to answer any questions if we have time.